Okay, never mind. 2 more seconds, guys. Let's just check. Going. Oh, it says. Okay, it should be live now. All right, it should be. Should be live. Wait for confirmation from the stream. We're live.
We are live.
All right.
Okay.
Hello, guys. Welcome to finally the Math 114131 revision seminar. We're very sorry for the technical difficulties. There was a class in here before us. We couldn't get in here to sort all of them out. But now we're going to get underway. So the plan for today is we're going to go through calculus. We've got a couple of wonderful, intelligent lecturers going to be taking us through the wonderful world of calculus. Just for anyone who's watching online, don't worry. The whole thing is going to be recorded, so we'll get that back to you later. And of course, everything. We will get the slides to you as well as soon as the sessions are done. They'll go up on the website. Because we've got beautiful written solutions on all of them, which should be very good. So Otto is going to take us through the first part of calculus. Then we're going to have the wonderful Jess taking us beyond, and then I'll be rounding us out depending on whether or not we have time at the end, which should be good. Please, if you have any questions, guys, for online people, we have a wonderful group of year 10s coming to join us. So shout out to them. They're stretching their understanding of maths today. But if you have any questions, please do shout out. Like, this is a revision seminar, not like a lecture. We're here to help you guys. We're here to all learn together, which should be very fun. But otherwise, aside from that, I'll hand over to Otto, who is going to steer us through the wonderful world of limits and stuff, and it should be good.
Awesome. Okay. Thank you, Tim. Let's see how this goes. Okay. Now, how do we get to the next slide? There we go. Okay. Now, we're going to start with inequalities, sets, inequalities, and functions. We're going to start off with this question. Now, quite simple. You might know a few ways to do it. We're just going to touch over them. First, up here, we have 4x minus 5, absolute value of that greater than 3. That is what we're looking to solve. Quick way you might think of it is divide both sides by 4. We get a center and then a distance from the center. Reinterpretation of the question into a number line. Okay? First, well, after that, we're going to dive into a bit more of an algebraically heavy method where we're going to consider the cases. Okay? Now, when we look at this question, the contents of the absolute function needs to, well, what the absolute function does depends on the sign of the contents. So we can consider our first case for when the contents are positive. In other words, greater than or equal to 0. To do this, we end up finding that x has to be greater than or equal to 514. Plug that in, and we have a positive interior. We can just wipe off the absolute value signs. Solving this, we get x has to be greater than 2. This means that we have a solution for x is greater than 2, given that x has to be greater than or equal to 514. So it's important to consider these conditions when we start looking at our domain restriction and then our solution condition, because, well, if we have an answer that is valid for x greater than 5, but we're only allowing x greater than 10, we can only say that the solution is for x greater than 10 as the intersection of the two domains, intervals. All right, taking the other case, we move on to x has to be less than 514. When we do this, the contents are negative, so we take off the absolute value signs and we put a negative out the front. When we do this, we end up with, well, solving it on the slides, x has to be less than a half. All right. Again, same argument. This has to fit inside of our restriction of the interval, the domain. So since x being less than a half fits entirely inside of x being less than 514, this gives us our full solution. Okay? All good? Happy? Awesome. Okay. Moving on to limits. Big jump. We will do our best. Now, we'll start with the epsilon m definition of a limit at infinity. Now, those of you here might be able to see a diagram of a function on the board behind me. I will just quickly draw it out just above here. this function quite clearly has a limit, okay? It approaches a certain value as x goes to infinity. Now, the way we formally define a limit at infinity is we say that, okay, if we pick some distance from this limit, anywhere, okay? Any distance from the limit that is greater than 0, we can find some value of x, we'll call it m, which all further inputs of x has to be closer to the limit. In other words, it always approaches the limit, okay? Always getting closer, always going to it, okay? Now, I'll be good with that concept. Any questions? All right, now we'll move on to the question. Using the epsilon m definition of a limit to prove that the limit at infinity of x squared minus 2 over x squared plus 3 is 1. Okay, so we are going to verify this limit by plugging it into the formula shown right here. Okay, and then we'll try and find an m that corresponds to epsilon so that no matter how close we get to the limit, we will get a interval of x for which we will always be that close to it. Okay? We all happy? Awesome. Now, we'll start, as we said, by substituting in. F of x is our x squared minus 2 over x squared plus 3, minus our limit is 1. When we take this subtraction, applying our algebra, x squared cancels off, and we end up with a minus 3 as well on the numerator, simplifying to minus 5 over x squared plus 3, all the absolute value. Now, because the denominator is always positive for our real numbers, x squared can never be negative, we have that the numerator determines the sign. Since we have minus 5 on the numerator, we flip that to a 5 and we take away the absolute value signs. Now, we're going to simplify this expression right here and turn it into 5 over x squared, a slightly bigger alternative, okay? Now, the reason we do that is so that we can find a corresponding m, not necessarily the smallest m, but a corresponding m for which we can find x within a range of error, which is our epsilon. So we will state that 5 over x squared will be less than epsilon, and then just by applying algebra to this, making x the subject and taking the positive case, we arrive at x has to be greater than the square root of 5 over epsilon, okay? Now, if we let this equal m, as stated just below, we end up with, for all x greater than m, x satisfies a certain distance from the limit, okay? Hence, we have validated the limit for all epsilon greater than 0 as required, okay? Hence, we've done the question. Are we happy with that? Awesome. Nice. Okay. Now, we're just going to find the limit this time. No more epsilon, no more delta, no more m. Just finding the limit, okay? So, first thing we see when we look at this question is find the limit of x as it goes to 0 of 3 times x squared plus the sine of 2x squared, all divided by x squared. The first thing we're going to do for this solution is kind of break it up, because we understand that the limit of a plus b is equal to the limit of a plus the limit of b, okay? Just really quick understanding that we can break up this limit into more parts. We can simplify it in that sense. So if we're all right moving on, we'll go to the solution. And so when we break it apart, this 3x squared over x squared comes out and turns into just 3, okay? And our other side of sine of 2x squared over x squared is left. Now, that gives us our 3, and then we're left with a little funky bit where we have sine of 2 times x squared all divided by x squared. Now, understanding that the sine of x over x, as x approaches 0, approaches 1, we can say that this number inside needs to match the number on the bottom for us to apply this identity, okay? So we multiply the numerator and denominator by 2 to achieve this over here, okay? As following by the next line, we can replace that with 1 as we've taken the limit, and we arrive at the limit of 5, all right? We all happy with that? All right, now we are going to jump into the properties of continuous functions. So I'll be handing over all of this to Jess. Thanks.
We got photo, thank you. Hi. So he just did our sets and our limits, and now we're jumping into the idea of continuity, the idea of differentiability. So I'll be talking about general properties, definitions, and then we'll be jumping into intermediate value theorem and mean value theorem. All right, and we'll cover a few more concepts here and there. But let's just talk about the definition really quickly. So the definition of a function to be continuous is that at a point x equals a, it is continuous if and only if you limit the function to a, you'll result in fa. Which, in terms of just plain English, that may not make too much sense, but it is conceptually fairly intuitive. So let me just draw any random graph here. So if I have any random graph, let's pretend that that's a graph, right? Naturally, if I approach a point x equals to a on this graph, if I approach it from the left-hand side, if it is continuous, it will approach fa. If I approach it from the right-hand side, it will also approach fa. If it does not do that, then we can assume that there has been a break in the function and hence is not continuous, right? Fairly intuitive definition. Hopefully there's no issues with that. Yep. But let's jump into the theorem, intermediate value theorem. Suppose that a function is continuous, all right? So this is us now working with the idea of continuity. Suppose that a function is continuous over this closed interval. If z lies between fa and fb, then there must be at least one real number such that fc equals z. Let's work with this in terms of graphs because I feel like understanding through graphs makes it a little easier, right? So let's work with this function, right? This function, we can see visually it is continuous between the closed interval, right? So between the closed interval a, b, the function is continuous, right? A being here, b being here, corresponding with fa and fb. And what we're basically saying is that if it is continuous, then there must be some value that aligns with any of these sets, right? Naturally, if it has to point from one point to another point and has to go through every single point, then every single point must have a corresponding value, right? Fairly intuitive, but let's work through some examples. So the first example we have is, consider a function. We're going to be finding the maximal domain, and then we're going to be applying intermediate value theorem, right? So what is a maximal domain? A maximal domain is the largest set of values that we can work with a function in. And when it comes to maximal domain, you're working with essentially restrictions, right? For example, if you have a fraction, you can't divide by 0. If you have a log function, you cannot log a negative number. You're working with restrictions. So first thing that I like to do, look at your function. What am I working with? Well, I have a trig identity, I have exponentials, I have log, I have a fraction, I have a lot of things to work with, right? First thing I want to touch is trig, because it has one of the strictest regions, right? Trig, especially a cos and sine, they can only be in between -1 and 1, right? So this statement, we know this to be true. Easy, right? So from this, we can decipher, okay, well, if I compare this to our denominator, add 2 to both sides, I can conclude that our denominator has to be in between 1 and, has to be in between 1 and 3, right? So I can conclude, okay, well, if it has to be in between 1 and 3, then I know my denominator is always positive. So I don't have to worry about, oh, what if the fraction is divided by 0? That is no longer something I'm worried about. So we don't have to worry about it for now. But what I do have to worry about is I still have this log function, right, guys? This log function means, what can I do with log? I need to log positive numbers only. Everything in my fraction has to be positive. How do I make sure it's positive? If I know 100% my denominator is positive, then my numerator has to be positive, right? My numerator has to be positive. All I have to say is, okay, well, 2 times e to the power of x minus 1, it has to be positive. Solving that, I know that it's going to be 1 on 2. X is going to be greater than negative ln 2, just using my log properties, right? And from there, I can determine that my maximal domain is just going to be negative ln 2 to infinity using my rounded brackets. Yeah? And that should be our part A. So if you guys just want to double check, confirm the knowledge, go through our working out again, this is all of it. No issues, I assume. Yeah, okay, looks pretty good. And let's go back to part B. Part B, by considering the intermediate value theorem, explain why f equals to 1. What was the intermediate value theorem again? We needed to suppose that the function is continuous, right? Remember, when we're using any theorems whatsoever, we need to show that the conditions are true for the theorem to even be applicable. So we need to show that the theorem is applicable. How do we know that this is a continuous function? We know it's continuous because it's only comprised of continuous functions. Exponential, cos, log, all of these are continuous functions. So we can say that this function is continuous, right? Now, how do we actually show the question though? Let's consider really quickly. Let's consider what is f0, right? And what we'll do is f0, just sub in x equals 0. And what you will find is, if you guys type it into your calculator, I'm not going to waste time and do it here. If you type it into your calculator, you'll find that f0 is 0, right? Same thing, try subbing in another number. I'm just going to pick 1 because easiest next number. If you sub in x equals to 1, type into the calculator, you're going to get something like 1.112 something, right? And again, this is a continuous function. We have shown for a and b is going to be between 0 and 1.11. Hence, by applying intermediate value theorem, we know that we have to pass by 1 at some point. And that would be our explanation. If you guys want to see a more eloquent written explanation, this would be it. Okay? So just giving you guys some time to process the question. Do we have any difficulties or are we good to move on? Cool. Hi.
So we want to do this in the exam for like F1, and F1 is not an exact point. Is that totally okay?
Yeah, that's fine. So you just say, you just use the approximation. Therefore, approximation equals this, but we know that that's greater than 1, so it's fine. Yeah.
I noticed that it's a maximal domain. What's the minimal domain?
No. So maximal domain, any smaller domain than the maximal domain would be just an imposed domain. So only considering the function in these values. Maximal is how big is the function now. Yes? Okay, cool. Moving on to next. Okay. Differentiable functions. So naturally, when we're talking about calculus and continuity, we want to talk about differentiability. So let's consider this question. Considering a function blah, given that the function is differentiable at x equals 1, find the values of a and b. Kind of standard math question, right? But we are given a condition. And when you are ever given a condition, you can kind of assume that you're going to be using it, right? If a function is differentiable at x equals 1, for these, right, we can differentiate them and assume that they're going to be equal to each other, right? So given that it is differentiable. So first, for our first function, if we differentiate that, we're naturally going to end up with 2ax plus 3. And for our second function, if we differentiate that, we're going to end up with 2 equals 2. And can you guys see how obviously x is going to equal 1 when we substitute that in? That's going to give us 2a plus 3 equals to 2. And can you guys see how very quickly, very easy, you guys can solve this, find a value for a? Half the question is already done. Right? But how do we actually find a value for b? Really quickly, that's going to be working out just there. I'm going to follow our working out here. So if a function is differentiable, we also know that it must be continuous at that point, right? By definition. And for it to be continuous, as I said earlier, for it to be continuous, the left-hand limit and the right-hand limit must be equal. So we can show that. The left-hand limit for this, just be very, very careful. When you're considering the left-hand limit, you must be considering the function that corresponds with x is less than 1. That's just the one thing I want to point. If you limit it to x equals 1, put that in, that's just going to end up with you having 2 plus b. Same thing with the right-hand limit, that's a plus 3, and then we can equate them. If we have an expression for b in terms of a, we already know what a is, we can solve for b. final conclusion statement. Therefore, A equals this, B equals this. Done. Yeah. So the main takeaway from that question is just, hey, remember that when you're given a condition, try to work with it. And second thing, differentiability and continuity is kind of together. They come as parallel concepts. All right. Moving on to the next part. So moving away from intermediate value theorem now, we're moving into mean value theorem. The mean value just says, suppose again that a function is continuous and differentiable. There must exist at least one real number C such that blank. Okay? And this is a formula that is provided to us. Right? Just one quick thing to note that every numeral that is here corresponds without interval. Alright? But let's look at the question real quick, and we'll explain the concept through the question. Assume that a differentiable function f on R is such that the diff of f is less than or equal to 1 for all x. Given that f2 is 2, show that fx is greater than x for all x is less than or equal to 2. Alright, first thing that I see is I have a domain. X has to be less than or equal to 2, right? Therefore, I can write my domain as this. X and 2, close brackets, right? This is the domain that I'm working with, and naturally, if I'm working with something, if I'm going to be using mean value theorem later, this is the domain I'll be working in. Yeah? Okay. So it is given that the function is continuous, so we don't have to worry about that condition for mean value, and therefore we're going to be trying to use it. So consequently, there must be a C such that we can apply all of this and find a value, right? So I'm going to do that really, really quickly here so we can also see the question. Subbing x and 2 into our formula, we're going to have f2 minus fx on 2 minus x equals to f dash 2, right? Pretty simple, fairly easy. And we are also given that f dash x is always less than or equal to 1, right? So we know that everything on the left-hand side must be less than or equal to 1, right? So we know, okay, well, if function has to all be less than or equal to 1, then I can say that this is true, right? Just skipping in the substitution first, moving everything, timing everything by 2 minus 1. We're also given that f2 is 2, and if f2 is 2, sorry that the working out is kind of all over the place. f2 is 2, we're going to be minusing 2 from both sides. Negative fx is going to be less than or equal to negative x. Therefore, fx is greater than or equal to x, hence proving the question is true. For those of you who want to see kind of a formatted version of that question, this would be your completely formatted, full marking. Are there any questions about that? Again, slides are given out, so if you ever like, I really want to look back on this, that's fine. We'll be giving out these slides to you guys. Any questions? Cool, moving on. All right. Okay, L'Hopital. Okay, so why do we use L'Hopital? Basically, you use this when you have to limit a function that is in a fraction that you can't really otherwise limit for some reason, right? So before I go through a bunch of conditions and a bunch of rules, let's just look at our example question. If you were given this question just by itself, and you were told to limit it, you can't just sub in h equals 0, because you're going to end up with a fraction on 0. It's just not going to work, right? That's why we have this rule. You can now limit something that you can't otherwise do without it. So let's actually go through some conditions and how to use it. First things first, f and g being our functions that make up our fraction, f and g must both be differentiable, okay? Second thing is that either one of these conditions must hold true. When you limit it to a number, whether that's 0 or something else, they have to either both approach 0 or both approach infinity. Not one approaches 0, one approaches infinity, other way around. Both approaches the same, okay? And then we can use this idea. L'Hopital's rule is essentially, if you want to limit something, then you can limit the diff of fx and the diff of gx, right? So let's actually work with this question. Evaluate the limit using L'Hopital's rule, and then we're going to be checking the differentiability, right? So before I jump into the provided solutions, let's just jump into what we would do if we just evaluated this limit as is, right? So obviously we know these are differentiable functions. We can use L'Hopital's rule as, let's check our condition. if you limit h to 0 for our denominator, obviously h is going to approach 0. For e to the power of negative 1 on h squared, you're going to have approach e to the power of negative infinity. That's going to give you 0. So I know, okay, my conditions hold true. How do I actually use the L'Hopital's rule? Let's get our numerator, and we'll differentiate it, right? That ends up with being, I think, 2 on h cubed, e to the power minus h squared, all on 1, right? And that will end up being 2 squared lim function on h squared, on h cubed. Because I don't see an issue with this. Can you now just sub in h equals 0? No, right? You can't, because your denominator is still 0. Okay, well, there are two options then. One, we can either use L'Hopital's rule again, or we're back to square one with the drawing. Let's try to use it again. What would happen if we use it again? You guys can try it. I'll give you a warning now. If you use it again, you're going to end up with another thing that looks like, hey, limit h to 0. You're going to end up with a random constant, e to the power of minus 1 on h squared, and h to the power of something, right? And if you end up with h to the power of something, that's always going to give you a problem. So back to the drawing board, back to square one, what can we do? The idea that you can do now is just deal with, okay, is there a way for me to manipulate this function so that I can use L'Hopital's rule? And the way that we're going to try to use here is we're just going to try flipping the function, right? So our numerator, instead of it being anything else, we're going to flip the entire function so that h to the negative 1 is our numerator, and then e to the power of 1 on h squared is our denominator, right? And then we're going to see L'Hopital's rule. Hopefully it works. If it doesn't, back to the drawing board. Okay, now I'm going to go down to our working out. So you guys can see here, that's exactly what we did as our first line of working out. We flipped the function. We realized that we couldn't work it otherwise. Using L'Hopital's rule, we go, okay, differentiate the numerator, minus 1 on h squared. Differentiate our denominator, as up with this. And we're going to times our numerator and denominator by minus h cubed, resulting in h on 2 e to the power of 1 on h squared. Now this is something that we can work with. There's no longer a 0 in our denominator, so we get 0 on infinity. We know that to be 0. And hence the limit of this function as h approaches 0 is just going to be 0. Right? Is everyone clear on the first part of this question? So general takeaway from this is that L'Hopital's rule, there are conditions that you must fulfill first. You must check that they're differentiable. You must check that as h approaches 0, they both approach either 0 or infinity. Get the conditions out first. If you use the rule and it still doesn't work, try manipulating the function so that it can. And one of the best methods to do that is just flipping it around. Okay? Let's move on to the second part of the question. Subsequently determine whether the function is differentiable at x equals to 0. So really quickly, that's just checking continuity. Checking continuity, again, continuity and differentiability kind of go hand in hand. Checking continuity is, again, left-hand limit and right-hand limit, checking that they're equal. You guys can very clearly see that that's both going to be 0, hence continuous. But to check differentiability, I want to recall this. Cool. So the diff of something is always going to be x plus h minus fh all on h. Okay? These are all that we should probably all know from high school. But if I'm checking it for x equals to 0, yep. X equals 0? Is it supposed to? Yeah. Okay. Checking it for x equals to 0, just cancelling out my x's, I'm left with this. Naturally, I know that f0 is going to be 0 just by looking at my function here. And then we're working with fh on h, right? Now I'm just going to scroll down to our working out. So fh on h, we know from the formula that that's going to be minus 1 on h squared all on h, and we're limiting that h to 0. And why are we using our first half of the question? Because only through the first half of the question can we find, oh yeah, we remember that, we remember doing that, that is actually equal to 0. So we're using the first half of our question to actually solve the limit. But that is how we prove that differentiability. And hence, because f-0 is equal to 0, Thus, the function is differentiable at x equals 0. Right? Any issues with that? Looking all good? Alright, cool. Inverse. Alright, so, okay. For inverse functions, we're kind of moving away from continuity for a second. Not really away, but we're working with a new concept. So, for a theorem, suppose that f is a one-to-one function, then the inverse of f will be unique, where the range and the domain are flipped. So essentially, if I just have a function, right? We know that the inverse of it is going to be kind of like the reflection of y equals to x. Say it looks like that, where the range of my original function is my domain of my inverse. My domain of my original function is my range of my inverse. Everything's flipped. Okay? Let's work through some concepts. So suppose that I is an open interval where I is differentiable and f dash x is not 0, then all of these conditions, right? So the biggest thing that I wanted to talk about is this bottom condition. The derivative of g is given by this formula, right? And again, this formula, I think, is fairly intuitive, but we'll again explain it through a graph just so we can see it visually, right? So working with this graph, oh, it's very small. Do you know how to add a page on this?
Yeah. Plus.
Okay, cool. So working with the function, I'm just going to draw my graph so it's a little bit bigger so we can actually work with it. Pretend that goes to the origin, guys. Just pretend. Okay. If I find the diff of this at a certain point, say it's going to be at this point where this happens, there's a change in x, there's a change in y. Let's say change in x, change in y, and I work with the inverse of it, then we also know that this change in, let's say y2, x2, the change in x2 for the inverse is going to be the same as the change in y, right? Change in x2 is going to be the same as change in y. Change in y2 is going to be the same as x. Why do we know that? Because again, everything is flipped for an inverse. Think again about how kind of the range is the domain is the range, right? And if that's true, then naturally, using kind of rise over run, if everything's flipped and we know it's the reciprocal, then we can say that this function is true, right? So it's fairly intuitive, but again, a graph might help to understand it. I found that throughout the entire course, if I never understood something, it was best to just draw the graph and try to figure it out from there so I could see everything. But let's work with this question. Given a function, lots of given functions. Part A, find all the critical points of f and determine their nature. So let's just work with A first, and then we'll talk through the other sections. So finding the critical points, naturally we know that to find critical points, we need to differentiate the function and then let it equal 0. So if you diff the function, you're going to end up with 2x plus 2x minus sine x squared. And we're going to quite intense. Okay. And then we can take out the, and then we can take out the 2x by factorizing it out, right? So we're left with 2x, 1 minus sine x squared. Right, and we're going to just let that equal to 0. So we're going to have to work it out here just so I don't have to write it in the corner. Having a various side, divide everything over. We know that x is not going to equal to 0 just because our domain that we're working with is 0 to 2 root pi. So we don't have to worry about x being 0 here. So divide everything over. We're going to end up with x equals to square root of root 2 on 2, square root of 10 pi on 2. All right. Really quickly before I go through that bottom section there, what I wanted to do is I also wanted to show you guys a way to do this in Maple, because I'm for one we're allowed to use Maple in our exams. Not sure for 1131, yes? Cool. I want to show you guys a way to do this in Maple, not so that you guys can rely on Maple in your exam, but if you guys ever have spare time to check your working out, it may be a way to do. So this is how you would actually solve for critical points using Maple. So you guys need to remember to use the package with student calculus 1. I chose to just remember it, but it's up to you. But if you guys ever want to check your working out, this will be the way to do it. Just input the function and use the function critical points. There are a lot of other functions. There's a reason why I kind of left all of this here. When you're doing your actual maple, you don't have to have this. If you guys didn't want all of these dots, you could just have the colon and it will not print all of that for you. But there are a lot of functions in here that are actually very, very useful. For example, if you guys can see, there's also like things like inflection points, extreme points, critical points, all of these commands that are really, really useful that might be worthwhile to get used to. We're not going to be able to go through like the maple version of every single question, but it is very worthwhile to
Plug Maple Workshop.
go watch the Maple Workshop on YouTube. It is great. Yeah, it is very worthwhile to know, especially because it's one of the only softwares we're allowed to actually use during the exam. Using it as a checking device is going to be phenomenal. But as you guys can see, it will give you 0 and the same value. Now, here is my issue with Maple, and here is why I went, do not rely on Maple, right? We got 0, a value, and a value, right? And those values were the same as the values that we got earlier, but can you guys see that we didn't get 0? Because 0 is an invalid answer, because it's not in our domain, right? We know that 0 can't be a valid answer if our function cannot be a 0, right? So there's the first thing. Maple is not something that you can fully depend on because there are some things that you may not have inputted correctly. It may consider answers or not consider answers that you may need. An answer that we need in this that isn't considered in Maple is actually the endpoint. So remember that we can't have 0, right? But we can have 2 root pi. We must consider that as a critical point because it's at the endpoint. But again, that wouldn't have been considered in the Maple, right? Alright, so to find the nature of these, we kind of skipped over the working out here. My bad. But to find the nature of this, you just look at the double derivative and sub in the points, figure out if it's positive, if it's negative, if it's 0. And what you will find is that if you have the double derivative of this, so you'll end up with something like 2 minus 2 sine x squared plus, oh, this is not a nice thing to div. Wow. Oh, okay, I'm not going to not say it. But if you diff it and then sub in your points, you're going to end up with both of them equal 0. Hence, they must both be points of inflection, right? This final part here, I want to talk about in part B. Just ignore it for now. I'll come back to it. Okay? But is everyone clear on critical points and especially how to use Maple with critical points? Biggest advice for Maple is always look back on your endpoints of your interval. It will help you a lot. Make sure you're checking whether it's rounded or closed. Okay, but let's go to copy. Explain why f is invertible, state the domain of inverse of function, and find blank. So there are a lot of elements to this question, right? But I'm just going to talk you guys through our working out. So from the previous part, we know that the diff of the function is 2x minus 2x sine x squared, right? And what did I say way earlier? Like basically, first question that I came here. First thing is that sine and cos is always going to be in between -1 and 1. Sine x squared is always going to be less than 1, right? And if sine x is always going to be less than 1, we know that this to be true, where 2x is greater than or equal to 2x sine x squared, right? Implying that everything in our function has to be positive, right? Fairly simple logical progressions here, right? We're just getting what we know is restricted and then trying to expand that out to our entire function, right? But from here, we can find that if the diff of a function is always positive, we can derive, okay, well, hey, if it's always positive, we know that it always must be increasing, right? If it's always increasing, it is a one-to-one function, right? Because for it to not be a one-to-one function, it must go back down for there to be 2 values. But we know it must always be increasing. So let's consider this really quickly. We know that it is going to be always increasing, and we know that there are 2 inflection points, right? So it's going to look something along the lines of this, right? Where it kind of just keeps skipping up and down. That's a very bad graph. Okay. Where it comes up, inflection point, comes up again, inflection point, up again. Right? 2 inflection points always increasing 1-to-1. Right? As it is continuous, again, because it's a composition of continuous functions, we know that it is invertible. Right? And that's just that first part of that question. That is, explain why function is invertible. Right? Yeah.
Does it matter that the derivative is not strictly greater than 0, but greater or equal?
Oh no, that's fine. As long as it's not less than 0, we know that it's never going to be decreasing.
But couldn't that be like, like point where it's flat and there's two values, two x's that have the same value?
It's a point of inflection. That is the point of inflection. So at a point of inflection, only one point is.
Alright.
Yeah, we've shown that the points are going to be these. Yeah. Okay. Cool. No, not a bad question at all. Not a bad question at all. Okay. Let's talk about what's the final question. State the domain of the inverse of the function. So what did I say earlier? The domain of our inverse is the range of our original function. And how do we find the range of our? So let me just say this real quick. It is going to be a lot easier to find the range of our original function than the domain of the inverse by itself. Simply because I look at our function, I don't want to find the inverse of it. I feel like it's going to get very, very messy very, very quickly. So let's actually just find the range of our original. How do you find the range of how do I find the range of our original? Well, we know that the function is always increasing, right? We know that it's never going to change in that. So I know that the leftmost x point is going to be my minimum. I know that my rightmost x point is going to be my maximum. That is my range, right? And hence, what am I going to do? I'm just going to sub in x equals 0 and x equals to 2 root pi into my function, right? Hopefully we have the working out for that. No, we don't. Of course we don't. That would be. Okay. But if you had the function right, again, it's just classic substitution. If that's 0 and with cos 0, that ends up with 1. You throw in 2 pi, again, same thing, right? You're going to end up with the values 1 and I think 4 pi plus 1? 4 pi plus 1? I think, yeah. Whatever the value is, that is going to be our minimum and our maximum for our range, right? And then hence we can say, well, okay, the range of this is going to be between 1 and 4 pi plus 1. If the range of my original function is this, then my domain of my inverse must also be this. Yeah, simple. All right. But remember, there are 3 parts of this question. We are still not done. Find the value of the inverse of the function as it is 5 pi upon 2. So what I want to do here is scroll down to the section. Okay. So again, I'm not trying to find the function for the inverse. Again, it's going to be very, very difficult looking at our original function. So how do we work with our original function to find this? Right? So really quickly working here, well, we know that, okay, that's not good. Let's try this. Okay, so our function was x squared plus cos x squared. We're going to solve that equals 5 pound 2. Why are we going to do that, right? Again, remember, range of domain, completely inverse, right? So when our original function hits a certain y value, then we can expect that for the inverse, when it is at that value, we're going to have our x of our original, right? Again, y and x are flipped, yeah? So we're going to try to solve this for this function for x. Easiest way to do that is just to make a substitution. I don't want to work with x squared. We can see that there's 2 x squareds here. So I'm going to say, let's let u equals to b. Let's let u equal x squared, right? U equals to cos u plus 5 pi 2. Equals 5 pi 2. All right. Anyone have any ideas on how we can solve this? I think that's all good. All right. What I want you guys to take a really, really quick note of is our values of cos. Again, what did I say earlier? When you are working with functions, the thing that you need to take almost the most importance to is the ones with restrictions, especially something like trig, right? Keep in mind, what is cos 5 pi 2? You guys can recall that cos 5 pi 2 is just 0, right? And naturally, if u is 5 pi 2, then I'm going to end up with 5 pi 2 plus 0 equals 5 pi 2. And that is going to be how I solve that, right? So that's what we're trying to say here. That was kind of like the step that we kind of dismissed there. But because cos 5 pi 2 equals 0, then we can say, okay, again, remember I made that u substitution. Can I answer your question once I finish it? Thank you. Because we know that, then remember I made that u substitution as u equals to x squared. So I know x has to be root 5 pi on 2. Everything is flipped. Therefore, I know that the inverse of the function at this point is going to be root 5 pi on 2. Right? What was your question?
What was the reason for choosing 5 pi on 2 again?
Oh, that was the question. Like, sorry.
Oh,
That was the question. Yeah. Oh, good. You're alright. I know I kind of like skim past the question sometimes. I get it. Alright. So that was part B, kind of a long section. But let's finally look at part C. How are we doing for time? We're doing alright. Okay, cool. Where is the inverse of the function differentiable? So to answer this question, let's quickly go back to some theory because it feels like it's been a while since we've looked at the theory. But again, whoa, where did the theory go? The function is going to be differentiable where this is true, right? Or in other words, if we look down here, the inverse is going to be differentiable as long as this condition is true. So we're looking for the condition at which this is not true, and that is where it will not be differentiable, right? So let's go down to the working out. Wow, this is a long question. Okay, so again, recalling that inverse function theorem, this is not defined when our denominator is equal to 0, right? And how do we know when is this not true? Well, okay. But we know that this is going to be true whenever we're at a point pi on 2, 5 pi on 2, or so on, right? But for specifically the domain, it's when these are the points, right? Yeah, because when we substitute this in, we're always going to get a value that equals to 0. And that's going to end up being a function. Remember, if you guys are confused about that a little bit, recall, look at this formula, look at the diff. Where is this going to equal to 0? What values of that are going to equal to 0? And what do I need to sub in for it to be 0? And from there, you will get this. How much time do you need for your section, do you think? Okay. I don't want to take up too much of your time because you have integration. So I'm trying to be really thoughtful of that. All right. If everyone's okay, can I move on to curve sketching so we can talk about asymptotes? Okay, cool. So, okay. For curve sketching, particularly oblique asymptotes, that's going to be kind of like the thing that we were introduced to recently that we weren't introduced to in high school. Suppose that A and B are real numbers such that A is not 0. And for a straight line, we can show that there is an oblique asymptote if this condition holds true. Again, let's talk through things through questions and diagrams rather than just straight up theory. So let's work with this question. What is curve sketching? You're going to be given a function, you're going to be told to sketch, right? What do we do? First things first is I like to find the axis intercepts. Naturally, that's just going to be substituting x equals 0, y equals 0. We've solved that for you here. And then naturally, whenever you have a fraction, you're going to work with asymptotes, right? So first thing, let's just find our vertical asymptote. We know that we can find our vertical asymptote when we're working with our denominator equals 0. Same idea, fraction can't be over 0, right? Vertical asymptote, that's going to exist at x equals to -2, right? So far, kind of high school concepts. We did this in 3 units and stuff like that. Let's actually talk about oblique asymptotes now. How do we work with oblique asymptotes? Particularly, how do we work with something like this function? What we want to do is something like this, right? So there are kind of 2 ways you can think about it. You can think of it either as long division, or you guys can think of it as just algebraic manipulation, right? But this is just the algebraic manipulation manner, where if I want to work with this, then I need to plus constant values between them so that I can actually simplify it, right? So you guys can see we've added plus 6x, and if you add plus 6x, you need to minus it. But if you work with the first 2 terms and separate them out into their own fraction, then you can divide everything by 3x. You're left with 3x, right? You're left with 3x. And same thing with minus 6x minus 12. And then you're left with 8 on x plus 2. So it's kind of just that algebraic manipulation where you're adding in constants, adding in variables to help us simplify this. If you guys aren't really too familiar with this, the best alternative is just long division, but it can be messier, it can be harder to type up on Mobius, right? But naturally, as you take x to infinity, this is going to end up becoming 0. So we're left with our oblique asymptote at 3x minus 6. And that's our application of that theorem here, right? So we know that the oblique asymptote occurs when our function minus blank equals 0, and we're limiting to infinity, right? But now, kind of final answer is, after all of this, after all these points, now you need to actually sketch, right? How do we actually do this? Well, let's just do things slowly. So, get our points. First things first, I like to draw in my asymptotes. Let's draw in my vertical asymptote first. X equals to minus 2. Let's say that that is here. X equals to minus 2, right? And then let's draw in our oblique asymptote. Oblique asymptote being at 3x minus 6, it's going to be about, say, here, right? Pretend that that gradient is 3, pretend that the intersection point is at minus 6. Minus 2 and minus 6, right? Somewhere into with this function. Now let's look at our x and y intercepts again. Remember our x and y intercepts, they're at minus 2 and plus minus 2 on the 3. So, okay. What that means is that we're going to be intercepting somewhere around here and somewhere around these points, right? So what my graph is going to actually end up looking like is it's going to come down from my vertical asymptote, have some sort of critical point, and then come back up and approach my oblique asymptote. Yx origin, right? And obviously annotating your x and y. Is there any questions as to sketching with oblique asymptote? Cool. Okay, now let's talk about kind of sketching with polar. So again, that's oblique asymptotes. We're working with polar now. Polar now is, instead of working with just x and y by itself, we now have definitions for, we're working with r and theta, right? But we define their relationship between polar and Cartesian as x equals to r cos theta and y equals to r sine theta, right? So again, let's work through a question, right? So there are no written solutions. Okay, I'll write them later. But the question we're working with is find the gradient of the function where theta equals to pi on 6, right? Do you mind giving me the sidewalk? Okay, but first things first, right? I'm trying to find dy on dx when my function does not have a y or an x, right? So I know in some way I'm trying to work with Cartesian, but I can't do it immediately, right? So what am I going to do? I am going to use my definitions from earlier, right? So what can I do here? You can see how if r equals to 6 sine 2 theta, then I know for this curve, I know that x equals to 6 sine 2 theta cos theta, right? Just by subbing it into the definition. And I can do the same thing for y, right? 6 sine 2 theta, sine theta, right? Simple. I'm going to leave that as concepts just for a second. We're going to come back to those lines of working out. But again, our issue is we want to work with dy and dx, right? So there are two ways that you can do this. To find dy and dx, there are two ways. One, either find an expression for y and x that only have y and x, aka find an expression of y in terms of x, find an expression of x in terms of y, and then you can just differentiate. But that seems a little tricky. The algebra here seems really difficult, especially since I'm working with sine, too many trig identities to work with. The alternative way is just chain, right? So instead of thinking of it as dy on dx, you can think of it as dy on some sort of constant times some sort of constant on dx, right? And we're going to think of it as d theta, right? Because can you see how from my equations that I have made, I can find dy on d theta. I can find dx on d theta. dy on dx by itself may be a little bit difficult though. Go ahead if you want to though. Absolutely not stopping you, right? But oh, I can't find the working out. That's fine. Okay, so let's find dx on d theta. If you were to differentiate everything for x, what you're going to get with is just, let's just leave 6 on the outside, minus 6 theta sine 2 theta plus 2 cos 2 theta cos theta. Oh gosh, I'm not going to have enough space. But that is my tip, right? And then what am I actually going to do with this? This currently kind of means nothing to me. But what I'm going to do is, remember, we need to find it at theta equals to pi on 6. Meaning I can just sub pi on 6 in, right? And that's going to give me some sort of constant, which I had noted down earlier, but I cannot find it in the absolute mess that is my notes. So I will try to find it in a second. Yeah, no shit. There's no way I can look through that. But you're going to get some sort of constant for this, right? Whatever it is. And you're going to do the same thing for dy on d theta. Again, getting some sort of constant. Once you've gotten those two constants, let's just call that p and q. So let's put at dx d theta, where theta is equal to pi on 6, it's going to equal p. For dy on d theta at theta equals to pi on 6, let's let that equal to q, whatever it is, right? And then what you're going to do is you're just going to substitute that back into our chain rule that we've specified earlier. But remember, that is not p times q. Remember, that is q times 1 on p. Q on p, right? Whatever value you get there, that will be your final answer. I'm so sorry that I do not have the actual values for you guys right now. Oh no, I do. I found them. Okay, cool. Cool. So dx on d theta, that's going to end up being 3 on 2. And dy on d theta, that's going to end up being 15 on 2. Go ahead and do the substitution and differentiations to fact check me. May not be correct. I'm 99% sure that I'm 90%. But yeah, you're going to get values for dx on theta, you're going to get values for dy on theta. Substitute that into chain rule, you're all good to go. Right? And that is our solutions. Sorry for not typing that in, guys. That's my bad. All right. But that is my section. Just a really quick summary. I went through continuous functions. I went through some curve sketching, intermediate value theorem, mean theorem, all that kind of stuff. Main thing that I just wanted to emphasize to you guys is whenever you are working with theorems, please make sure that your conditions are actually true so that you can apply the theorem. But I'm going to be passing off to Tim for the next section.
Yeah. Let's give them a clap. I just wanted to say, like, I am so proud of these guys. They've done an absolutely phenomenal job. They've been spending the last couple of weeks grinding like the entire course to try and be able to get it to you guys, to present it to you all. But yeah, I'm going to be wrapping us out with the last couple of topics of the course, which is wrapping out with integration. Then we'll take a look at our log functions and exponential functions, and then we'll look at hyperbolic trig functions, which should be very fun. Now, integration, what we do in this course is not a ton of like actual integration itself, and we look at a couple of like theorems that are going to look at, because the way that 1A sort of sets up the course is we like kind of to build it up from fundamentals rather than to, I guess, actually do the practical stuff, which is kind of annoying, right? Because unless you're like a pure math student, you're probably not going to do a ton of like building stuff up. Just so I can get a bit of a vibe. Who here actually studies maths? Oh damn, that's a couple of you guys. Who studies engineering? That's what I thought. Is sorry, did I get some? Okay. Who does like civil eng? No one. Electrical eng? Hell yeah, my condolences. I'm sorry, guys. Who does quantum eng? That's what I thought. Josh. What do you guys study? Flexible, actuary, data science. Hell yeah, big slay. Also sorry, I do say slay, so you're gonna have to deal with that for the little next bit. My condolences. And it started off unironic. Oh dear, Lockie, can you come fix the guy? Thank you. Guys, big claps for Lockie, and I'm sorry to the people online, you're gonna have to wait 2 seconds, we'll get that back online. It's coming, don't worry. But yeah, so integration, also just so I can get a bit of a context, who did 4-unit maths in high school, or like the equivalent? Okay, yeah. Get keen for 1B, because basically the whole integration course in 1B is just like 4-unit integration. Integration here, we have a little bit of 4-unit where we've got, who didn't do 4-unit, by the way? Dude, you're all nerds. Come on. Okay. Yeah, okay, so we do have a little bit of like 4-unit integration here, but a lot more of the integration here is looking at it from kind of an abstract perspective, which is fun because like that's not what you're gonna do in engineering, except for you guys who do math. It sucks to be you. You'll do a little bit more of that stuff. Anyway, Integration is basically like the inverse of differentiation, right? So differentiation is where we look at a function, we take its gradient. Integration, as I'm sure you're all aware, is where we take the area under the curve instead. Now, in formal, big, fancy language that engineering students, you can just like let it leave the side of your brain after this course, is we have the first fundamental theorem of calculus, which says that the integral of something, and actually I don't like this black pen, sorry. I'm gonna switch it to, does anyone have a preference for color? Do we have any hot colors? Let's do purple, guys. Let's be a bit quirky. Okay, so we say that the integral of whatever this function is equal to big capital F, where it's defined by when you take the derivative, you get the original function again. Woo! Crazy, crazy stuff. It's basically telling you in fancy words what you learned in high school, which is integral, differential, derivative, like they're pals. They like each other a lot. Our second fundamental theorem of calculus is how we actually use integrals in a like non-analytical, more like actual math sense, which is when we take the integral, we chuck two bounds on it, one being our upper bound, one being our lower bound, and it's sort of like if you've got some kind of curve that you're integrating over, let's say this is like your point A, this is your point B, it's basically just telling you we're going to find the area under the curve between these 2 points. That's what our bounds mean. And from there, when we take the integral, we get some sort of function and we sub those two bounds in. Coolios, we've been doing that since we were like 16. Very hot, unless you weren't, in which case, doing it since whenever you learned basic integration, which is cool. Now, from there, you can actually learn a fairly funky, cool trick, which is where they try and spice up a lot of these questions from. Just for more context, sorry. Who's doing 1131 and who, anyone doing 1131? Nerd. Who's doing 1141? Hell yeah. Okay, we're all doing 1141. 1151? Yeah, nice, nice. My condolences. Okay, so yeah, so they like to chuck a couple of these bad boys in because it's like this kind of question here where we're taking the derivative of some kind of gross function and making you do stuff. The reason for that is because otherwise you would just be able to solve this question using your basic like understanding of integration rather than actually having to use the theorems that they want you to learn, which is this fundamental theorem of calculus. So what are we doing in this situation here? We're trying to use the second fundamental theorem, sorry, to actually solve this question here. So we're taking the derivative of an integral that goes from 0 to sine of h times cos of t over the square root of 1 plus t squared dt. That's very exciting. Now, guys, put your hand up. Who can integrate that for me? Come on, guys, you did 4 unit. Integral of cos of t over the square root of 1 plus t squared is so easy. It's probably some like ridiculous, like we stressed like integral. You probably chuck it in Maple, and Maple's like, frick you, I'm not doing that. Anyway, yeah, so basically they've given us some horrific looking integral that we can't actually integrate, so we're going to have to actually use their fundamental theorem of calculus, which is very fun. Now, in order to do this, oh, I got squared paper, that's hot. Cool. So we're going to use the fact, we're basically going to combine our two theorems together to get a bit of a cheeky rule that we're able to use instead. So if we remember back up here, when you take the derivative of our like integral, which is basically what we're doing here, right? Like if big capital F of x is equal to our integral, then the derivative of that is the derivative of our integral, right? What are you doing, Ronald? Ronald's running around for the people online. He's being a bit of a cheeky boy. Yeah, so we take the derivative of that, and that's basically telling us that it's equal to our original function again, except it's not actually that true. Well, they're lying to us, okay? Is that updated? Oh yeah, okay, cool. Basically what's actually happening is when we take that derivative, because our function is no longer just the function that we started off with, right? We've got these bounds that we have to consider as well. When we take the derivative of it, we have to use the chain rule. So what do I mean by that? I'm going to do a little bit of theory before we actually jump into this question, just so I can sort of show it to you. But essentially, if we differentiate some kind of integral, like let's go back up to that basic like integral from a to x, f of x dx, and we've got f of big capital F of x equal to that. Well, then the derivative of this, i.e. us differentiating an integral, because we know that this is equal to whatever our big f of x is times this like upper bound, which is in this case x, minus the derivative of our lower bound, sorry, minus the like integral of our lower bound. Does that make sense to everyone? That's essentially just using our second fundamental theorem of calculus. And sorry, I should chuck the derivative sign out the front. When we go in and we take the derivative of this function, we then have to use the chain rule, which is very fun. So we're going to say we're taking the derivative of big F of x minus the derivative of big F of little a. Does that make sense to everyone so far? Okay, now what we have to do then is we want to take, and I've realized that making my upper bound x is a little bit confusing. So what I'm going to do instead is I'm going to switch my upper bound. Please bear with me. I can do this because I'm the one with the pen. I'm going to change my upper bound to like x cubed, right? So that then means in here, it's going to be x cubed here and here. So when we take the derivative of this, when we're taking the derivative of big F of x cubed, we need to take the derivative of both big F, but because we're using the chain rule, we also have to multiply it by the derivative of little x cubed as well. Does that make sense to everyone? Essentially, it's kind of like you can imagine, we don't know what big F is, but this could be like, sine of x cubed. And when you take the derivative of sine of x cubed, you have to take the derivative of like both the sine and then also the x cubed. Does that make sense to everyone? Hot. Okay, so let's do that. So in this case, because we're doing it in abstract mathy terms, the derivative of big F, remember, is just little f. So it's going to be little f of our x cubed times then by the derivative of x cubed. Does that make sense to everyone? Which, because you're all big 4-unit nerds, everyone say it with me. The derivative of x cubed is 3x squared. Let's go. Good job. You passed your HFC. Very proud of you all. Band 6s all around. And then same thing for the other one. Now, a is just a random constant, so you differentiate it, you get 0. Or let's actually say it's like the derivative of whatever f of a is, because let's keep it abstract. But yeah, it would be like dA dx times little f of a. Does that make sense to everyone? Cool. And this is actually like kind of a general trick that we can use for whenever we're solving these questions. And just as a side note, almost 100% guaranteed that one of these questions will rock up in your final because, the 1A lecturers aren't sneaky. They chuck these ones in every single time because it's the only interesting thing that they can do with these theorems is use these kinds of questions. So just remember, it's the derivative of your upper bound times like the function of your thing with the upper bound subbed in, minus the derivative of the lower bound times your function with that lower bound subbed in. So let's actually do that. Cool. So in order to do this, we have to use that, I guess, general rule where we can say that if I call this, let's call this f of x. We can say that f of x is going to be equal to this function here with our upper bound subbed in. So cos of sine h of x. Also, side note, have you guys done hyperbolic trig functions yet in your lectures? You just started them. Okay, TLDR, we'll actually get to them later. But your sine, cosh, and tan, also, that's just what I call them. Like, there's no, like, official name. I just think that that's fun, because shine sounds really cool, even though the H is at the end. They're not even trig functions, but they are called hyperbolic trig functions because when you do calculus on them, they follow very similar rules to the trig functions, and that's why we call them that. They're essentially, for the purposes of this one, when we differentiate shine, we get cosh. When we differentiate cosh, we get shine. That's why we call them shine and cosh, I guess. It's even better than trig functions. You don't have to keep track of the negative. Like, it's really lovely because it's shine and cosh gives you cosh or sine, shine. Anyway, yeah, we sub it in, so we get cosh of shine of x over the square root of 1 plus shine of x squared times the derivative of shine x. Sorry, guys. The shines are getting to me. I'm a bit shiny at the moment. Okay, yeah. So when we differentiate shine, we get cosh. So we'll multiply it by the derivative of that upper bound, which gives us of x. Does that make sense to everyone? And then we do likewise for the bottom one, which is going to be minus cos of 0 all over the square root of 1 plus 0 squared. But of course, then we multiply it by the derivative of 0, which is It's 0, yes. So it's going to disappear anyway, so we don't care about it. We don't love you anymore. Which just then leaves us with cos of sine x times cos x all divided by the square root of 1 plus sine h squared of x. Now one of the really fun things that you will learn when you go through the sine and cos in your class is you may remember your normal trig identities have, like, you know, cos squared of x is like the square root of 1 minus sine squared of x. Sorry, just sine squared of x. Because sine and cos, I reckon, are nicer than normal sine and cos. You don't even have the negative there anymore. It's 1 plus sine squared x, and sorry, that should be not square rooted, which means that this bottom part is actually just cos of x as well, which is really hot. Which means that that's cos of sine of x times cos of x all divided by cos of x, and then you cancel those two out, which just leaves you with cos of sine of x. Does that make sense to everyone? Lovely, cool. But yeah, so that's a very common, I guess, question that they'll ask a lot in these kinds of paper in your like final, is just that kind of funky integral, and you just use that process. It's the derivative of one times you sub it in, and then the derivative of the second one, and you sub it in as well. Anyone have any questions on that? Lovely. Okay. We have the full answer, and as you can see, oh, that's like, oh yes, gives you what we got at the end. Cool. So then the next integration topic is integration by parts, which, as being big 4-unit nerds, you should all be familiar with. Which is very nice because when these ones come up, you should be like, yay, free marks. I mean, most of calculus, to be honest, will be free marks for you guys anyway. But now you know when you see an integration by parts question, you can do it quite easily. So this should be a nice revision for you guys. We're doing integration by parts to evaluate the integral from root 3 to 0 of tan inverse. Sorry, I just realized I quickly skipped over the formula. This formula, if you're unfamiliar with integration by parts, is essentially just a rearranged formula of the chain rule. So it's like if you differentiate this thing, you get that part as derivatives, and then we like rearrange it and chuck an integral sign on. This is kind of spoilers for next term, but integration by parts, the reason they teach it to you now is because some people won't take 1B, and integration by parts is basically like the most powerful integration technique you'll ever learn. So even though everything else that you will learn next term is sort of like helping you out in kind of specific situations that pop up a lot, integration by parts is kind of like the big hammer that will hopefully, provided your integration skills are like half decent, will like destroy any integral that you come across, which is very fun. Now, in order to tackle an integration by parts question, all we have to do is we have to look at our integral and assign one thing to be u and one thing to be v. Most of the time, the tricky part is just figuring out, of what we've got there, what can we already integrate? And whatever we can already integrate, that's what we assign to be v. Because if you look up here, v is still getting integrated. So if we can't integrate v, then that kind of leaves us in a bit of a hole where we have nowhere to go from. Now, the main problem with this question is the inverse of tan is probably not an integral that you just know off your head, unless you're all nerds, which, I mean, you're here. So there's a solid chance that maybe you do know tan inverse off the top of your head, but I don't, all right? So I'm going to say I don't know what tan inverse is, so I'm going to set that to be my u, because while I don't know what tan inverse is, I don't know what the integral of tan inverse is, I do know how to differentiate tan inverse. But like, that's my entire integral, right? What do I have left to set as my v? Does anyone have any suggestions? Uno, lovely. I can set 1, right? Because even though it's not here, if you zoom in really close, there is actually a 1 times tan inverse that's chilling there. That's always chilling there. It's always watching. And so as a result, we can let our v be equal to 1. So then, and that's v dash. So going from there, we have to differentiate u and integrate v. So we can say the derivative of u is going to be tan inverse differentiated. What is it, guys? Come on, guys, you did 4-unit. It wasn't that long ago. All right, it's 1 on. Beautiful. 1 over 1 plus x squared. And then when we integrate 1, we get v is equal to x. So then we can just sub that into our formula, right? We pretty much just do formulaically. We say the integral of this thing is equal to u times v, so these two multiplied together, so x of 10 inverse x minus the integral of x, which is x times the derivative of u, which is 1 over 1 plus x squared, which is still not super nice, but hopefully is something that you can integrate if you remember how to integrate your log functions. We also need to remember our bounds because we do actually have bounds here. So we've got like 0 root 3, and this one we need to, oh, I didn't mean to do that. We need to integrate this from 0 to root 3. Sorry, we need to evaluate that from 0 to root 3. Also, I'm looking at this, and please accept my humblest apologies for how goddamn awful my handwriting is. Thank you very much. I appreciate it. Okay, so now subbing in our values, right, we're going to have root 3 of 10 inverse of root 3. Anyone remember what 10 inverse of root 3 is? That's great because I didn't remember it. Lovely, root 3 times pi on 3. I'm taking your word for that because genuinely, I mean, I've got a calculator here, but it's all good. And then we actually have to integrate this. Anyone have any suggestions for how we can integrate x on 1 plus x squared? Josh. Beautiful. So we can recognize that the derivative, like the thing on the top, is almost the derivative of the thing on the bottom. All we have to do is times it by 2. If we do that, we can't be illegal. We have to multiply everything by 1 and 2. And then suddenly, the thing on the top is now the derivative of the thing on the bottom. So if we integrate it, we get the natural log. So setting that, we can then do root 3 pi on 3 minus a half ln of 1 plus x squared. Evaluated between root 3 and 0, subbing all that in, root 3 times x, sorry, whatever that thing is, minus 1/2 of ln 1 plus x squared, which x squared of root 3 is just 3, so it's 1 plus 3, which is 4, and then, so that's going to be ln of 4 minus ln of 1. What's ln of 1, guys? It's 0, lovely, so that just disappears. And so our final answer, I think, this has all been quite quick, is root 3 pi on 3 minus a half of ln 4. Does that make sense to everyone? Hot. Okay, yeah, so when you see these guys, they usually will pop up earlier in the exam because they're fairly straightforward. You can honestly also, you have access to Maple, bung it in Maple if you can't be asked to do the actual integration by parts, and then that will probably work as well, which is very cool. And look at that, guys. We smashed it. Round of applause for us. Good job, guys. Okay, that's integration by parts. Anyone have any questions on that? Lovely. Okay, other fun thing that we have to do is figure out whether or not integrals converge, because we can sometimes have integrals that have fun little things that go from 0 to infinity. And we need to figure out, oh, is this going to converge or is this going to diverge? Now, in order to do that, we have to use a whole bunch of little tests that we have. My favorite test is one that we call the p-test that I reckon we might use on this one. But essentially the idea here with most of these questions, just to sort of contextualize this, right, is we don't know whether when you integrate this, it gives us something that goes off to infinity. Like, let's say, for example, you integrate 1 on x from like, actually you can't integrate it from 1, but let's say you integrate it from like 1 up to infinity, right? When you take the integral of this, that's equal to ln of x from like 1 to infinity, but ln of infinity is infinity, right? Which means that this thing goes off to infinity, which is great or not great, depending on what the circumstances are. Versus if we have instead the integral from 1 to infinity of 1 on x squared, well, when you integrate this, that gives you minus 1 on x from 1 to infinity, which is going to be like 1, which does actually converge. And that means when we look at our integrals, sometimes it's not actually like super obvious as to whether or not something is going to converge or not. Does that make sense to everyone? Cool. Luckily, there are some fairly nice tricks that we can use to help us figure out whether or not something is going to converge or is going to diverge. And honestly, there are two, like, You probably went through like tons of them in the lectures. There's honestly two that I would say are the ones that will save your life most of the time. And they are, the first one, I don't know if I wrote them up here. Yes, I did. The comparison test. So basically the idea here is we have some gross looking function here. 1 plus sine x on 3x squared. Gross looking function, I don't know whether that converges. I don't know whether that diverges. What I do know though is that sine is smaller than something. What is sine smaller than? 1, right? Sine is always smaller than 1. So I can say that this integral from 1 to infinity of 1 plus sine x over 3x squared is less than just subbing in 1 instead of sine, because I know sine is always less than 1. Just as a quick refresher, the reason for that is sine oscillates between 1 and minus 1. It's a cute little wiggle. 1 to infinity of 1 plus 1 over 3x squared. Does that make sense to everyone? And the reason that that was so powerful is now suddenly, instead of having gross looking integral over here, I have this is equal to 2 on 3x squared integral there, which is pretty damn easy to integrate, right? Like that's just like 2 on 3 times 1 on x squared, and that is something that you know the integral of, and hell, we just did it up here, right? We know that that converges. Does that make sense to everyone? Cool. Okay, so using that, we now know that f of x is less than something that does converge, and therefore, it's sort of like, imagine that you're in like a line of traffic, right? How many of you guys drive? Or have driven at some point? Average, oh, that's more than I had. That's more than I had. How many of you guys have your Ps? Let's go. One person carrying the team. All right, good stuff, good stuff. No, average, how many of you guys have your Ps? Do any of you have your Ps? Dude, it's okay. I got my Ps like a couple months ago, and now I'm like, yeah, it's okay. Like, I swear half of like the STEM faculties, it's because we're too focused on doing important stuff, like convergence theorems. Like, who needs to go and explore the world? Okay, yeah. So it's sort of like when you're driving, right? If the car in front of you stops, you also have to stop, right? Because you can't just keep on driving. That's how you lose your Ps, all right? If you just keep on driving through that car. That's essentially the idea behind the convergence theorem. If you know that something bigger than you also converges, then obviously you must converge as well. And likewise, if the car behind you is going really fast and there's only one lane of traffic, all right? You know, even though it's against the road rules, you would probably also start accelerating as well, because you don't want that car behind you to catch up, okay? And likewise, if you know that something that is smaller than your function does diverge, i.e. something that's smaller than you goes off to infinity, therefore it also makes sense that you probably also go off to infinity. Does that sort of make sense? Okay, so what we've just done here is we've shown that something that is bigger than this function, i.e. something larger than this function, stops. We also must stop because the car in front of us has stopped, therefore we should stop as well. Does that make sense to everyone? Lovely. And yeah, here we essentially just said sine is less than 1, which means that this function is less than 2 on 3x squared, and therefore that thing converges. And honestly, I will say that almost all convergence integral questions boil down to essentially try and get your integral to look like something over x to the power of something, either bigger or smaller. And then you can use your second rule, which is called the p-test, to determine where it converges. Because essentially it turns out that if this power p is less than 1, so if p is less than 1, yeah, then it means that when you integrate it, you get something that's like log or bigger than log. So when you chuck infinity in, it actually does diverge. Whereas if p is greater than 1, you get like the integral of 1 over p, where 1 over x to the p. If p is bigger than 1, then that means it's like, damn, how do you do basic integration? Guys, I'm actually struggling here. This is embarrassing. It's like 1 over p minus 1. X to the p minus 1, and if p is negative, it's probably going to have a negative out the front as well. Don't judge me on that, but basically because p is bigger than 1, p minus 1 is like not 0 or is not negative, and so therefore it is something that is going to go to 0 when you sub infinity. Guys, why did I say I might have made a mistake? And suddenly everyone is like freaking 40 glasses. Like, let's make sure, let's analyze everything. It's okay. But does that make sense to everyone? That's essentially like 90% of your convergence integrals are just going to boil down to find something that it's bigger than or smaller than, and then use p-test to say, oh, this converges or doesn't converge. So going back up here, we could have said, okay, because like this is because this is similar to a p-test with p equals 2 and 2 is bigger than 1, that means it converges, which is lovely. Yeah, guys, I'm going to do the rest of the lecture like that. Cool. Does that make sense to everyone? Oh, what did I miss? Please tell us. Please test. That's pretty. I don't know. I'm sorry, guys. My pun game's in the floor at the moment. Okay, so that's integration. That's, I guess, the like 3 main things that you would look at and have questions on in your exams. So either integration by parts, those funky ones where you differentiate it and then do fun stuff with it. No, wait, sorry, I already gave you the answer to that one. My bad. Pretend you didn't see any of that. Rewind your mind back a couple seconds. Sorry, you did this one. Exact question, guys. All right, come down the front. Josh, you're coming down. We're walking through this. All right. You were paying attention in the lecture, weren't you? Hey. All right. Okay, so we've got. So guys, welcome up, Josh. He's coming to walk us through. So, okay, so just to contextualize before we keep going. The next 2 topics are essentially looking at specific kinds of functions, because a lot of the stuff that you'll deal with in like broader engineering. Is this the year? Are you guys year 10s again? Dude, the year 10s are back. Can we get some round of applause for the year 10s? Coming back to integration. Let's go. Okay, so your last couple of topics are basically just looking at specific functions. Now, you've probably already looked at like ln and e to the x in high school, so we're not going to look tons at it next. And then the last functions you look at are the exponential and log functions. Sorry, the hyperbolic trig functions. And yeah, so the hyperbolic trig functions are pretty straightforward for the most part. Like, it's just the same rules as sine and cos. And if you forget stuff, you can look at their definitions. Anyway, the one thing that I guess is kind of funky with the exponential and log functions is where you have functions that look like this and you're asked to find the derivative. So you've got y equals x sine of x, and you want to figure out what dy dx is. Now, whenever you're solving these questions, there's a lovely trick you have to use, which apparently you guys looked at in the lectures. Now, Josh, what did you do? What was the trick that you had to use?
Okay, so like, say we got.
It's just rejected, Josh. It's like, no.
Why is it?
It's on eraser thing.
Okay. So like, a to the power b is like equal to b ln a or something, yeah?
Yes.
So we're gonna apply this thing imaging, yeah, to our function. So now y equals to e to sine x ln x. Wow,
Oh,
crazy.
okay.
Right now,
Did you guys actually do this? Sorry, just
so much easier.
Josh is killing it.
Differentiate, yeah.
Now, looking at this, you might claim that this is easier to differentiate. Josh, I'm going to have to disagree. I look at this and I say, yucky, sine x times ln x, like taking, actually, that's not too bad, never mind. What would you do go from here?
So we can just, we know that basically ddx efx equals to like f dash x e to fx. So we could just apply that. We need to do product rule.
Okay,
to
I'm going to
sine x
x
ln x.
That's 100% valid. That's 100% valid. Do you want me to show you a very hot and sexy trick to make it a little bit easier?
Do you use log?
You do use log, right? This is the log
That's
and
the other
exponential.
way,
topic. Yeah, you know. Guys, round of applause for Josh. He smashed it. And I just want to point out, this 100% is a valid technique, and honestly, it's not even that bad. Like, it's not even that hard of a technique. The only reason I cut him off is I want to show you like another trick, and he was doing it his own way. He wasn't doing it my way, okay? And I want to show you my way. Okay, essentially what the trick is because we have, like, we're going to exploit a very cool property of the log function, which is if we have log of, like, you know, some a to the power of b, we can rewrite this as b times like A. Sorry, B times ln of A. Does that make sense to everyone? The reason that that's so hot is it means we can go back to y equals x ln, sorry, not ln, sine of x. And we can just take the natural log of both sides. So if we have ln of y equals ln of x to the power of sine x, because we've got our stuff to the power of sine. No, you guys can comment if you want to learn maths. It's okay, it's okay. They don't like math. Okay, because we've got x to the power of sine x, right? What we can do is we can chuck that sine x down the front. So we can say that that's now equal to sine x times ln of x, which is actually very similar to what Josh was doing. You could just actually come back to this step and move the e across to the other side, and now you've essentially got the same thing. So good job, Josh. Smashed it. By the way, context for everyone, Josh is like part of my subcommittee. I'm not just bullying a random person. I'm allowed to do this. Okay, so yeah, we've got this very hot expression, ln y equals sine x times ln of x. And now we're going to use another cool technique called implicit differentiation to differentiate this. Because it's going to be so much easier than if we had differentiated the OG function. Doing that really quickly, I know we kind of brushed over implicit differentiation beforehand, but implicit differentiation is where we just remember y is actually like a function of x. So when we differentiate y, it's like the same as doing chain rule. So doing that, it's like doing ln of like some function of y. If you differentiate that, you end up with the derivative over the original function again. Yes, so it's going to be whatever the derivative of y is divided by y is equal to, and then we use product rule really cheekily on this. That's going to give us sine x over x plus cos x ln x, and then to find the derivative, all we have to do is multiply across by y, which gives us dy on dx is equal to y times sine x on x plus cos, sorry, I'm running out of space, cos x ln x. And then to round it up, we remember, oh yes, sine was actually equal, sorry, y was actually equal to this, so we sub that back in. So that gives us x sine of x times sine x on x plus cos x ln x, which is still pretty gross, but I guess it was a lot easier to solve this using like by natural logging both sides because it simplified it down into a product rule. Does that make sense to everyone? This would be really useful as well if you're trying to differentiate something that's like x to the power of x to the power of x, for example, like having some gross ass power, chain power. It's very nice. Anyone have any questions on that? Lovely. Okay, I'll see you soon, Josh. Okay, so our last topic that I really want to quickly look at, I'm sorry, we've got 10 minutes left, and I hear another class lining up, is our hyperbolic functions. I've been hyping them all up. Our beautiful Shine and Kosh. Now, we call them the hyperbolic trig functions, and that's a lie. They're not trig functions at all. They're actually exponential functions. The reason that we call them trig functions, I said it earlier, is basically just because when you do calculus on them, they behave a lot like trig functions, and they also have a lot of identities that are very similar to trig functions. Now, they're defined by cosh x equals half e to the x plus e to the minus x, and shine x equals half e to the x minus e to the minus x. Will be wrapped up in 10 minutes, don't worry. Okay, cool. Well, guys, we will be speeding hyperbolic trig functions. Okay, so hyperbolic trig functions are yeah, sorry. We did have this room booked until 2, if that's okay. Yeah. Sorry? Oh, 3, I'm sorry. 3 o'clock, the end of this hour. Anyway, so yeah, your trig functions look like this. Because you've only just learned them, you won't be asked any like ridiculously stupid hard questions on them. Like this is probably, I guess, kind of the upper echelons of hard questions you might be asked on the hyperbolic trig functions. And with these, essentially all you're going to do is just sub in your definitions for Shine and Kosh. So like go back to what they're equal to, sub them in terms of E, and then you'll have an expression that is in terms of E that you can actually evaluate. So in this case, it simplifies down to just 1 on e to the x, which is e to the minus x, which is pretty easy to solve. Does that make sense to everyone? Aside from that, there's a whole lot of like nice identities that you can use with Shine and Kosh that are very fun. that are very also look a lot like trig functions, because that's why we call them the trig functions. But anyway, that's our hyperbolic trig functions, and that's all of calculus of 1A in 1 hour. I hope that you have learned something very useful. And also, can I just like to thank the incredible Otto and the wonderful Jess for taking us through the first part of that. They absolutely killed it. We're gonna have another one of these for algebra tomorrow from 3 to 5. So if you want to come back, year 10s, I'm looking at you guys. You're gonna learn some algebra. It's gonna be hectic. Go smash your exams. 3 to 5. Sorry, did I say 5 to 7? Okay, we will fix that because I'm pretty sure it's 3 to 5. We will rectify that. Thank you for pointing that out. Anyway, we have to be out to let these wonderful people actually learn more stuff. That's fine. All good, all good. That's all fine. Thank you all for coming. We'll see you guys next time. All right. And thank you to everyone on YouTube as well. Bye bye. Oh, that's the wrong mouse. Let's end the stream with it.